gonna get started. I hope everyone had a good Thanksgiving. Today we're gonna have CJ. He's a PhD student here at CMU, a math PhD student. So he's gonna talk to us about chasing nested convex bodies. And well.
Right. Thank you. I want to start by dedicating a talk today to the memory of one of the co-authors, Michael Cohen, who very unfortunately passed away in the process of writing this paper last year. He was only 25 years old. So he was out with Sebastian Bubeck at Microsoft Research, and Anupam and I Skyped with him, or Skyped with the two of them. And when we got on the call, I immediately recognized his voice as a high school classmate of mine. And thinking back to then, he had this unforgettable, kind of unapologetic nerdiness to him that he just really loved anything he could learn and didn't really care if it was weird or what anyone thought about him. And it seems to have served him very well. From what I understand, though he had a very short career as a researcher, he had a very productive one. Okay, so the topic of today's talk is going to be a problem in online algorithms, which has a really nice geometric flavor to it, chasing nested convex bodies. So the way it goes is you start at some point in Rn, Rd. I'm going to use d as a dimension, and I'll just illustrate everything in 2D. So you start at the origin, and I'm given a convex set. And so now I have to place some point in that convex set, and I move to that point, and I'm charged whatever distance I moved. Now once I've gotten to that new point, I'm given a new convex set, and again I have to place some point in that convex set. I'm again charged the distance, and I just keep doing this until whatever time I'm out of sets. And since this is an online algorithm, we're always going to be comparing to the offline optimal, and what that looks like is basically you just see all of the full sequence of the convex sets that you're going to get up front, and then after looking at them, decide on kind of the optimal path here. And as you can see, it's always going to be shorter when you have the the full knowledge ahead of time. And so we're always going to be comparing our algorithm to whatever this opt is. To give a formal definition of this problem, you're given convex sets kt in Rd. Again, d will be the dimension throughout this talk. And you have to choose points xi in the convex set ki in an online fashion. You have to specify what xi is before it is revealed what k sub I plus or ki plus 1 is. And then the cost of your algorithm is just the sum of the successive distances between each xi and the previous xi. And the goal here is to find an algorithm with a small competitive ratio. The competitive ratio basically looks at, for any instance, how does my algorithm do, divide that by what the optimal cost on that same instance is, and I look at all instances in the world and take the worst one, and that gives me the competitive ratio. And I want some algorithm with competitive ratio as close to 1 as possible, since obviously I can't get it any lower than 1. And the historical motivation for this problem comes from another problem, more general, kind of more important problem in online learning, or online optimization, which is called MTS. And the way this problem goes is I'm given functions now instead of sets, and they're convex functions. And each time I'm given a function, I have to place some point. And I'll be charged for playing that point. I'll be charged whatever distance I had to move to get to that point, plus the value of the function at that point. And this is more general and can be used to describe a lot of, like a kind of a whole family of online algorithms or online problems. And convex body chasing is specifically looking at what the geometry has to do with this problem. And you can just imagine that if I gave kind of the same function just translated a bunch of different times, so the actual shape of the function is playing some role, but just the fact that I'm translating it is also playing some other role. And the convex body chasing problem was introduced really just to isolate kind of the role of the moving minimum of that function. And it can also be seen as a special case of MTS if you just let fi be the function which is 0 on some convex set and infinity everywhere else. Then if you want to have a finite cost, you have to go somewhere in that set. And the charge will be just the distance that you're moving. It's also somewhat related to another fundamental problem in online algorithms, which is called k-server. Some of the methods in the more general problem that apply to k-server can also possibly apply to this problem. So in this talk, I'm going to talk mostly about the nested version of this problem. And here, the convex sets are all contained one within another. So I'm always going to a smaller and smaller feasible set. And I get down to something kind of small at the end. And if I look at what's going on in the offline setting, I'm eventually going to have to place some point in the smallest body, but that's already contained within all the other bodies. So the best thing to do is just go immediately to whatever point I'm going to be at for the rest of time, and that's just the closest point in the final body to where I started. And this is really what makes the nested version a much easier problem to deal with, is that we have a very good idea of what opt is doing. In the general version, we don't have such a good idea of what opt is, so it's harder to kind of nail down the competitive ratio. But here we have a very good idea, and we just have to kind of bound what. OK, so I will try to go 1.6 speed or so. So quickly, let me summarize the results. So the most important things on this slide are the square root d lower bound, which I'll show in a minute. Our work is the bolded one on the third line, which was the first polynomial competitive algorithm for nested chasing. And then this last result is actually just a couple of weeks old, which is basically optimal for nested chasing, and it was the first algorithm that works at all in the general case for any dimension. And I'm also going to talk about this second result. It's kind of an intermediate idea towards the idea of this talk. So the first section will just be a few warm-up ideas. I might go through that pretty quickly. The second thing I want to talk about kind of the two algorithms that we thought of en route to coming up with the algorithm that we actually used. And then I'll actually talk about the algorithm that got us polynomial competitive ratio. And I will, depending on time, give some or none of the analysis. Okay, so the first thing just important to have in our back pocket is the lower bound of square root d. And the way this works, I'll show it in d equals 2, is you start with a hypercube, and you're just progressively forced to go to a smaller and smaller face of this hypercube. So at first, I have to go to the right side of this square, and then I have to go to the top point of that side. And so offline, I had to make this kind of, I had to move in every coordinate direction, but online, I do it all at once, and I get square root 2 in this case. This can easily be generalized to d dimensions to get square root d. Okay, so just to have a sense of what's going on here, greedy might be an idea that you thought of to do this, just always project onto the convex body. It actually isn't a very good one. This example shows that if you basically give this kind of rotating half circle, you'll have the algorithm go all the way around the circle and basically end right where it started. And you can get it as close as you want by having small rotations. But if, sorry? No, so this is a bad idea for the general case. It also happens to be a bad idea for nested, but you're right, this is not a nested instance. In this case, opt should just go right to the center and then sit there for the rest of time. So while the algorithm is unbounded, opt is O of 1. And so this is not competitive in the general case. In the greedy case, it actually is competitive, but it's d to the d competitive. And the lower bound is still exponential. So I'm not sure where the truth is, but it's still not very good even for the nested case. So this next slide is pretty important. So what I want to do here is now actually change the problem a little bit into just a form that we can describe easier. So the first reduction I want to make is I'm going to assume that and I'm again talking about the nested case now. So I'm going to assume that my convex body is bounded. And it has, say, diameter 1 or some constant. And also that the optimal solution pays at least some constant amount. So now all I can look at doing is just, I want to have a bounded total cost when that can scale with the diameter of the first set. And that will give me a competitive algorithm. For this case, since opt is bounded below. And in general, the way I can use this to solve the entire problem is by doing some sort of guess and double strategy, where I look at, say, what opt is initially, make a sphere of twice that radius, and play just on the intersection of that sphere with all the convex bodies I get. Then when I run out of room on that intersection, now opt has to be outside that sphere. So opt has doubled. I can double the size of my sphere, and I lose some constant factor, and this gives me a competitive algorithm for the general case. Now the next reduction I want to do is I'm actually not going to wait until I'm done on the sphere. I'm just going to go until the diameter has been cut in half. And if I have an algorithm to do this, then I just apply that over and over and over again, kind of resetting every time I've cut the diameter in half, and I get a geometrically decreasing cost, so I lose like a factor of 2. And again, all I have to do is have this Titan algorithm, and I have something for the entire problem. Just to quickly recap kind of the important ideas here. One is that I have this square root d lower bound. 2, greedy is not the right algorithm to do here. We're going to kind of use it as a sub-algorithm later. And 3 is the most important point, is that we're just trying to have the diameter of some bounded set. And if we can do that with a bounded cost, then we're good. Right? Any questions so far?
Why wouldn't that having give you a constant competitive ratio instead of root? Oh, I see. Root d is constant.
Sorry? Why wouldn't what give you constant competitive ratio?
It doesn't grow with n is the point.
D is the parameter here. Right? Square root d is getting worse as dimension gets.
So in 2 dimensions, the third algorithm, having a diameter, is going to give you a constant competitive.
Right, but it's going to, you're saying if you have this algorithm, the tightening algorithm with, like.
No question. Does that algorithm give constant competitive ratio?
No, it has f of d competitive ratio.
Fix the dimension.
Yeah, in dimension 2 it has constant competitive, but the dimension is the parameter that we're interested in. We want to know how the competitive ratio increases with the dimension. But yes, it does have competitive ratio something in dimension 2. For every dimension it has a fixed competitive ratio. It just gets worse as the dimension gets bigger.
It's not as good as square root of d.
No. Ours is going to be linear in the dimension.
Is it correct that if you fix the dimension that you actually have a constant fixed competitive ratio?
Yes.
That's clear.
No, we have to give an algorithm for that.
Yeah, it's not obvious. That's what I'm saying. That's what I'm asking.
Yeah, no. I mean, if it were obvious, then I wouldn't be giving this talk.
Oh,
I think.
Sure. I was curious. Is the thing like that it is competitive, that you can make it competitive, or is the thing how to make it in the best possible form?
Right. So until this problem was posed in '93, and until a year and a half ago, there was no known algorithm with a finite competitive ratio in d equals 3. Or in the nested case in d equals 3, or in general, either.
Okay, but this geometric decrease, that does give you a constant competitive ratio.
So the Titan algorithm is also, the cost of this is going to be dependent on the dimension.
But he's saying, but you just said that for decades it was open whether there was a constant competitive ratio.
In D3. So you just said it was an open question.
This
and now
it's
a trivial algorithm.
This algorithm relies on the existence of an intermediate step that can get you from the full diameter to half the diameter with a constant cost. Before a year and a half ago, there was no known algorithm to do even that.
Okay.
Thanks. Okay. So next part I'm going to talk about this is kind of the genesis of our idea, is these 2 other algorithms that we tried and why they didn't work. So the first one is the centroid algorithm. Here I'm just going to move to the middle of the feasible set every time. You can define the center in a couple different ways. It turns out the way that seems to work the most nicely is going to the centroid, just the center of mass, or the average location of a randomly sampled point.
Maybe misunderstand, but it's never to advantage to move to interior of a set.
So
go to the boundary.
Right. So that's correct. That you're not right. You just by the triangle inequality, you should always go to the boundary. The reason that we want to do this is that once we're sitting in the center of the set, then in order to force us to move again, you have to cut off a lot of the feasible set. So like maybe you could technically modify our algorithm based on this. But I think it would break down after 1 or 2 steps. It would no longer kind of make sense what you're supposed to do. And it turns out that this is very important for the analysis, that you're going to be losing a lot of volume. So, I mean, just to show this, you keep kind of moving to the center, and as you can see, every time we're lopping off some constant fraction of the set, and we're making progress really fast. I mean, this set is shrinking very quickly. And after only a few steps, in this case, we've decreased the diameter by a lot, and it seems like we're making good progress. Yeah?
So to be clear, you only move if you're not already in the convex.
Yeah, I'm assuming that every set is making me move, because otherwise I just ignore that.
No, but first set could be your initial polygon is still be very close to the very first set. Then you move a lot to the centroid, but the optimal would be hardly move at all, and
Right.
you're already not competitive.
So that's the bad example that I'll give in just a minute. So first, let me at least pretend to justify this algorithm. So there's a theorem of Grunbaum that says that I am in fact cutting off a constant fraction of the volume, right, every time, which means that the volume is dropping over time, is dropping exponentially. And I'm hoping to get some sort of exponential drop in the volume in order to have the diameter, because if I have the diameter, then I'm kind of having the width of the set in kind of every single direction. And each one of these costs, I'm just kind of forgetting how much it costs, and so since I know my set is bounded, I'll take the cost, the O of 1 cost each time, and hope that I'm going to get something like linear, since that's how long it takes for the volume to shrink. The problem is that the diameter isn't necessarily going to shrink if the volume is shrinking. And so here's the bad example. I give some sort of trapezoid which is weighted to one side, so the centroid is over to the right here, and then using the bottom part of the trapezoid, I give a rectangle which forces me to move back to the middle. And as long as I've got kind of some positive distance in the direction of the height of the rectangle, I can keep doing this. And I'm just going to go back and forth forever and not get a competitive algorithm at all out of this. And the problem here is that I'm not actually getting the diameter anything below whatever the width of this rectangle is. And so at a certain point, it's basically just moving a constant distance back and forth instead of moving, I should be moving much less than that, right? The optimal is just moving in a straight line down. So centroid has this nice property that the volume drops quickly, but that's not enough to give us the diameter. To drop quickly, it stays constant. So kind of inspired by this bad example, the next idea is a recursive algorithm in which we're going to do something where we just say, okay, at a certain point, I'm just not going to move back and forth, right? What was bad with that last example is that I kept moving all the way back and forth when I didn't need to. So let me just fix one direction and move only in that direction. And that's going to keep me from having any sort of back and forth, since in that one direction, I'm only moving in one way. Right? So to give a somewhat more formal definition of this, in R1, I'm going to just do the greedy algorithm, which is in fact the optimal algorithm. It has a competitive ratio of 1. And then in RD, what I'll do is I'll fix D hyperplanes right at the beginning. And think of these as like the coordinate hyperplanes. And then I'm going to go through each one of these and recursively run my D-1 dimensional algorithm on the intersection of that hyperplane with the feasible set. And let me kind of show what this looks like. So I'll start off with fixing these two hyperplanes. And first I'm just going to focus my attention on S1, the kind of vertical direction here. And I'll have a second picture here just because, again, in the mind of the algorithm, I don't care what's going on in the second dimension. I'm only caring about what's going on in the first dimension right now. So when I get some set that it does whatever in 2 dimensions, but I'm just going to look at this kind of red dark thing as the feasible set in 1 dimension. And so now the algorithm sees I have this point right here and that feasible set up there, so I'm just going to project onto it. And I'll mirror that move in the real world. I'll get another set, kind of do the same process here. And so now eventually I get some set that doesn't intersect my, my subspace at all. And so I'm going to say, okay, I'm done with this subspace. Now I'm going to move on to some point that's in the next subspace and just restart the process from there. So now I'm going in my second direction. And again, I kind of have this real world, algs world picture going on here. I get some set that cuts down my subspace. I project onto it. And I run out of that subspace, move to, say, the center of the new set. And now I really have made a lot of progress. Because if you look at the original picture where I drew my subspaces, I necessarily have the feasible set contained in one of these quadrants defined by those subspaces. Since I can't intersect either of those 2 black lines, it has to be in one of those quadrants. And now I've made progress. So the diameter has gone down a lot, and we're happy. And this is exactly the algorithm that Nikhil Bansal and his co-authors gave. It was the first competitive algorithm given for nested chasing. And so yes, greedy also does work, but we didn't know that until after they gave this algorithm. The issue with this is that it's really, really bad competitive ratio. It's D to the D. It's about D factorial squared. And this is actually a little bit worse than greedy. It's also d to the d, but this happens to be worse. The reason, there's kind of two reasons why this is bad. So one is that every time I do this recursion, I'm doing it on a set which has a roughly the same diameter as my full dimensional set. So I'm incurring the full cost of the competitive ratio in d minus 1 dimensions. And I do that d times. So now I've paid d times the competitive ratio in one less dimension. And what's even worse than this is actually the diameter only goes down by a very small amount each time I do this. So I have to repeat this process order of d times in order to get my diameter down as far as I want to. And now I've recursed d squared times. And that's why, since I'm multiplying basically by d squared on the competitive ratio in one lower dimension, that gives me d factorial squared. So it works, but it's not pretty. So just to kind of summarize these two algorithms, and then we'll...
First algorithm that had a competitive ratio?
Yeah. Yes. Again, so greedy was certainly a known algorithm beforehand, but the proof that greedy is competitive at all came after their paper was published. So Centroid had this nice property of volume dropping quickly, but it didn't do much for the diameter. Recursive Greedy, it allowed us to kind of keep this shape balanced, or be shrinking in all directions, but every time we recursed it cost a lot of money, and the diameter was shrinking too slowly to really be making progress in a meaningful way. So now the next thing I want to do is give the algorithm that this talk is really about, which is d log d competitive. And it was going to kind of combine the two ideas that we had from these two algorithms. So the first thing is, okay, instead of playing the greedy algorithm in the recursion, we're just going to play the centroid rather than projecting every time. And this is, I would say, a smaller idea, but it's going to allow us to kind of maintain this volume drop property, which is going to be important in the analysis. The more important idea is that before we kind of fixed our subspaces up front and said, I'm going to go in this direction, then this direction, then this direction. Now what we're going to do is we're going to start playing, and only once we get to some situation where we have a skinny subspace, and if some direction in which the feasible set is very small, then we're just going to restrict to that subspace. And this is good for two reasons. So one is that it's cheap. When we're doing a recursion on some subspace in which the feasible set is very small, then the diameter of that set is much smaller, and that kind of offsets the competitive ratio from a lower dimension. And that'll allow us to do recursions for cost little o of 1. The other thing that's really important here is that we actually get a separating plane between that subspace that we were recursing on and the feasible set once we're done. And I'll show this in a couple slides. And what this means is that we're actually getting a cut which shrinks the convex body specifically in the directions in which we have a large set. And I'll show this kind of on the bad example for the centroid algorithm on the next slide. So I first want to just make sure it's very clear what I mean by a skinny subspace, because this is an important idea to really understanding what's going on with this algorithm. So I first define the directional width of some convex set. And that's just, I fix a unit vector v, and it's the maximum inner product I can have with some vector in that set with that unit vector v. And I'll define a skinny direction to be roughly one in which the feasible set has directional width, something like 1 over d squared. It ends up not mattering, it's just 1 over poly d basically. And I will maintain this set S, which is going to be a span of skinny directions. And basically what's important about this is all the directions, I'm kind of using skinny directions to define the set, and all the perpendicular directions are not skinny. And F is going to be, I'll call it the fat subspace. It's the orthogonal complement of this. And F has the property that along every direction in the subspace, the feasible set is fairly large. I'm going to skip this slide because it's not that important. It's just illustrating what I just said. So the algorithm, I will kind of give the algorithm. Let me actually do the illustration first, and then I'll come back to the formal definition. So I'll show you kind of the same example that we had earlier that centroid did not do well on. So I'm going to start off by playing the centroid. I'll do that a couple times. And now once I've gotten down to this convex set, I say, OK, if I look at this direction, I'm pretty skinny in that direction. So now that I've gotten to this kind of skinny direction that I can move in, I'm going to only move up and down until I can no longer do that. So now I'm going to kind of play this recursive algorithm the same way I did it in the recursive greedy. I'll go to the centroid instead. It's not terribly important for illustrating right now. It'll be important in the analysis. And then, so now when I get some convex body that doesn't include that, now I've actually shrunk this feasible set by a lot in kind of the right direction. I can draw this new separating hyperplane, which is separating that subspace that I was recursing on from the current feasible set. And that's parallel to that subspace, which means I've really gotten a cut that cuts the fat direction. So let me just go back now to do this properly. So I'm just going to run this process until the diameter gets as small as I want. I first have to ask if the set of skinny directions is non-empty. If there are none, then I'm just going to play the centroid. But if there are, so I'm going to kind of anchor my point in time in order to run this recursion, which is running the lower dimensional recursive centroid algorithm on the intersection of the feasible set with the affine subspace parallel to the skinny directions that's intersecting wherever I'm sitting at time t. And I'll do that until that goes empty. And then I'll move to the centroid. And then after I've moved to the centroid, I'll update the skinny directions if I need to, so that when I go back up to the beginning of this loop, if I have a new skinny direction, then I'll be doing my recursion along that as well. All right, any questions about how this algorithm works? Makes enough sense? OK. So skipping through this again. The main theorem of this talk is that this is, in fact, a competitive algorithm, and it's a good competitive algorithm. It's d log d. And as a reminder, we had this square root d lower bound from this kind of hypercube example. And so that shows that this is within square root d of optimal. So we're pretty happy about that. So the outline of this proof, really the most important step here is we define a potential. And this is where it's going to be important that we're playing the centroid. The potential is defined as the volume of the projection onto the fat direction. So I take whatever my convex body was, I have my subspaces in which it's fairly large, I just flatten it out onto those subspaces and then see how big is, what is the volume of that set. And I'll have this kind of on the top of the slide so you can refer to this as we go. What I'm calling a step from now on is I'm basically taking a higher level, like I'm only focusing on the d-dimensional picture. So I'm imagining that whenever I do a recursion, that just kind of happens by itself. I'm ignoring that, and all I see is I recursed, I got my separating hyperplane, which is parallel to that direction that I was recursing in. I moved to the centroid, so I got a cut, I moved to the centroid. That's all that I'm thinking about doing in a step. So I have to show two main things. One is that the cost of one step is constant, which is in stark contrast to the original algorithm where the cost of a step was the competitive ratio in a lower dimension. And then I have to show that there are not that many steps, only d log d, before I have a body which is small in the sense that the diameter is actually shrunk. I can only do this so many times before every direction becomes skinny. And so I have d log d steps, each one has constant cost, so d log d total cost. All right, so focusing on a single step. So to show that the cost is O of 1, the centroid move that I'll do at the end, so that's just a single step, it'll cost constant because I'm in a bounded set. But the recursion is going to be cheap because I'm doing it specifically on a subspace where every direction of that subspace is very small. So the diameter of the subspace on which I'm recursing is something like 1 over square root d. It's a little bit bigger than that, but it's small enough that it's not going to be an issue. Now, since I'm doing recursion, I'm assuming inductively that I can play that lower dimensional body with cost at most d log d times the diameter of that body, which is little o of 1. So that's how I'm able to recurse, get this cut that I want in constant cost. And now the potential is dropping by 1 minus c. And so recall Grunbaum's theorem, which says that every time I cut off the centroid, I'm losing a constant factor off of the volume. So the important thing here is that when I get this cut, kind of, since this cut is parallel to the skinny directions, when I project it down into the fat directions, it's the same cut. So I'm cutting off the point, which is just the kind of the projection of that subspace that I was moving in. That subspace projects to the centroid, and I cut it off. So I am actually cutting off, if I'm just looking in the world of the projection onto the fat directions, I'm actually cutting off the centroid. And so that's how I get a constant decrease in the volume of the projected body.
Can you explain the recursion again? Is the algorithm recursive?
Yes. Yeah. So what I do is I take my skinny directions, I look at the intersection of whatever that subspace is with the feasible set, and I'm playing, so that's in some lower dimensional space. I'm playing.
Until you play the game in the same algorithm.
Yeah.
In the lower dimensional set until it no longer exists in that subspace.
Yep.
And you start over again, back up to the top level.
Exactly.
And move to the centroid.
Exactly.
Okay.
Yeah. All right, so this is what's going on in a single step. And I'm going to I need to carry over this, this 1 minus c drop in volume to now trying to figure out how many steps we have. So the main idea is going to be to look at how this, this potential is changing over time. So every time we take a step, I'm going to let m be the number of steps we're taking, since it's technically different from t, but every time we take a step, we get a shrink in this potential. It can increase, however, because if you think about what happened in kind of the skinny rectangle example. So at first, our potential that we were looking at was the entire area of the rectangle because everything was a fat direction. But once it got skinny, so the volume of that was actually pretty small since it had a dimension in which it was very short. But once we added that as a skinny direction, so now the projection is only onto the long direction, and we're no longer measuring the area, we're measuring the width. And so that just jumped up a lot, since we're no longer multiplying by some small number. And it's important that we have some bound, which is just a quote from another paper, where they show basically that this can only increase, there's some bounded increase every time you lose a dimension from the fat subspace. So in total, we end up losing about d to the d is the kind of multiplicative increase we get as a result of shrinking the fat subspace over time. And the last important part is that the final potential can't be that small. And the reason for this is, if I just rewind one step before I'm done, so I still have some fat direction. And when I look at the kind of projection onto the fat subspace of this, of the feasible set, it's got to be large in every direction, since by definition, these are the directions in which this body is large. And since it's large in every direction, it contains some large enough ball, which has size something like, or has radius something like 1 over poly d, and therefore it'll have volume something like 1 over d to the d. And that gives us a lower bound on the final potential. Right, okay, so yeah, the fact that this is t minus 1, not t, is not important. So I'm just taking those 3 facts that I kind of mentioned off the last slide, leaving them there, and we'll put this all together and get the competitive ratio. So what I'm looking at here is really the thing in the middle is the ratio between the final volume or the final potential and the original potential. And what's going on here is, so the bound on the right is just from the volume of the lower bound on the final potential, and the fact that the original potential is the volume of some bounded set, so it's constant. Now the d to the O of d that's the possible increase that I'm getting over time due to the taking away dimensions from the fat directions. And the 1 minus c to the m is the shrinkage I'm getting over time due to all these cuts that keep cutting off the centroid of the centroid of the projection. So the total change that I'm getting, or the total shrinkage I'm getting, is at least 1 minus c to the m times d to the O of d. And now if I just divide both sides by d to the O of d and take the log, The sign flips since 1 minus c is less than 1, and I get m is less than O of d log d. And remember that m was the number of steps, so I took at most d log d steps, each one cost constant, and that gives me d log d competitive ratio. Right. Any questions on that? Yeah.
So part of the point here is once a fat dimension is gone, it's gone forever.
Yes.
So you only have to look at increases from up to d fat.
Yeah. So the way that this is done is I maintain the skinny subspace and just keep adding vectors to it over time. I never like move it at all. I'm just adding vectors to it, and f being its complement just shrinks and shrinks. Yeah. All right. Let me skip this in the interest of time and just give a couple open questions. So as I mentioned at the beginning, just a couple weeks ago, we got the first competitive algorithm for chasing non-nested convex bodies. It's exponential, and we have the square root d lower bound, so it's still a question, what's the truth? Is it polynomial or is it exponential? I'm not really sure. I don't really have a guess one way or the other. The other thing that all of the work on this ignores is, can we actually implement these algorithms in any reasonable amount of time? We did things in this algorithm such as find the centroid and just asserted that we have that, or find the projection onto the fat directions, which are not so simple to do in the real world. So that's all. Thank you for listening. I'm happy to take questions. Yeah.
So coming back to this remark that Boris made at the beginning about, in reality, you never want to enter this set. So you gave this example how just a simple centroid algorithm can be forced to zigzag back and forth.
Yeah.
So suppose you just had the simple centroid algorithm, but that would stop at the set. It would just go towards the centroid and stop at the set. Do you actually have an example where that performs badly, or is that just hard to analyze?
Right. So the problem is that we don't have this drop in volume in the analysis. I mean, so I think what happens here, is there a chalk around?
Supposed to be.
I think it's a fire hazard.
Okay, so I think the problem is that, right, so you project onto the set in the direction of the centroid.
And I could even do this thing where, like, I'll only change which centroid I'm walking towards once that centroid is cut out. Like, I could really just make something which dominates the other centroid algorithm. There's like some ghost that moves
Right.
towards the centroid whenever it has to, and then you're just walking towards the ghost and stopping at the boundary, right? And so that certainly does at least as well. But the question is, like, is there
a lazy version?
Yeah.
Lazy
Right.
version of his algorithm. There's no reason not to do that.
Right, keep going. It does become a little bit of, it definitely becomes harder to just state the algorithm, especially with the recursion. And I don't want to be, like, I want to kind of have my fixed subspace.
Is there a counterexample that shows that the recursion is even necessary? Like, is it possible that just this thing, just moving towards the centroid, stopping the boundary, actually works?
Here's a counterexample.
Okay.
With the ghost, you can force the ghost to move all the way to the centroid by just shaving off more and more of the convex set until it's gotten all the way to the centroid. And then only once it's like at the centroid do you actually remove the centroid and it starts moving to the next point. Like having all the convex sets just barely include the centroid.
But so the example that he showed, though, where you have to zigzag back and forth, most of the zig occurs inside the set.
Right, but imagine there were intermediate slices that removed more and more of that to force you to. Oh, I see.
Well, but now, like, the angles of the zig and the zags are all different. Yeah.
Well, what I mean is, if you keep going towards the old centroid, then it doesn't matter that the new set has a different.
Oh, okay. Maybe you're saying that, like, this ghost thing can be made to perform as the non-ghost thing. Fine, but still, it's not clear to me that there's a counterexample to just the argument to the algorithm of going towards the centroid, stopping at the.
Yeah, that one I'm sure.
Let me think about that, and nothing comes to mind immediately. It would, I mean, effectively, it seems like it would end up being something like greedy. Right? Is once I'm making these like tiny little steps towards the centroid, I'm almost projecting onto the set, and then I should be able to do something like this rotation example. I mean, in there, in the rotation example, I would be moving towards the center, not towards the top. And also, the rotation example only gives you it does give you a linear lower bound on greedy if you just like restrict it to the nested case. Yeah.
What's the best known competitive ratio in dimension 2?
Like, what's the number?
Numbers.
I don't remember if the Friedman and Linial paper actually puts a specific number on it.
But it's not square root of 2.
No. Actually, there was a paper just put on arXiv yesterday that claims that it's a little bit worse than square root 2.
Also, it's a better example.
So there's another kind of sub-problem that people have looked at is line chasing, where every set is a line. And they gave an example, and this has a competitive ratio of 3 in every dimension. And they gave an example of this where the competitive ratio is like 1.5 or something like that. Or where they gave a lower bound of 1.5 or something like that. Yeah?
Can you tell us a bit about how you arrived at this potential?
I mean, so when we started doing this, the idea was to use the potential of volume. And that's where the idea of the centroid algorithm came from. And then it was just, once we saw, okay, we have to like recurse on these skinny subspaces. We had to have some way of dealing with the fact that like the potential is like artificially too small if I have a very thin feasible set, right? It somehow doesn't measure my progress if I have this minuscule volume, because I could literally give you a set which has 0 height in that dimension. Right? It could just give you a line. And I haven't necessarily saved myself much if if I'm living in some high dimensional space and I just went down 1 dimension, but my potential went to 0. So if I remember correctly, so the original algorithm that we had actually used the volume, and it was defined a little bit differently to not let the subspaces ever get that skinny, basically. And then we had some argument about, the volume can't get that small because the actual set has to contain a little ball or something like that. Any other questions? All right, thank you for affording me 2 extra minutes in light of the fire drill.